Kia ora. We're going to have a look at page 43, and page 43 is looking at how to deal with the Poisson distribution when you've got experimental data. So let's have a look why. The table shows the probability distribution for the number of wasp nests found in each hectare of a large section of bush in a national park. So see how it says experimental probabilities here. So pretty much what it means is they must have gone out and taken data, so they would have got like a hectare, each hectare, what is that, H capital A or something, I don't know, right? And then they would have counted the amount of wasps inside that hectare, and then they may have done this like 100 times and then given experimental probabilities. So half of those hectares had no wasps in them. One of those, 0.16 of them had one wasp, 10% of them had two wasps nests, and 0.08 had three wasp nests. So yeah, this is an experimental distribution. Okay, what is the experimental probability that there is at most, definitely worth looking at most one wasp nest per hectare in this section of the national park? At most one wasp nest per hectare in the section of the national park. So what is at most one? So that would be the number 1, obviously, but also there could be 0. Okay, so that means what we're going to do is we're going to have to look at 0 and 1. So from our experimental probability, we just get this. So it's just going to be 0.51 representing all of the hectares that had no, like the proportion of hectares that had no wasp nests. And then we'll add on the proportion of them that had one wasp nest, which is right here. Right, so that means that 0.67 or 67% of these hectares had at most one wasp nest. Right, so we're using the experimental probabilities. Okay, let's go to the next question. What is the experimental probability that there is at least one, but fewer than 4 wasp nests per hectare in the section of the national park? So at least one, so that means the easiest way is generally just to write a list of the numbers. So at least one, so 1 is counted, 2 is counted, 3 is counted, but fewer than 4. So this actually means x is greater than or equal to 1, and this one means x, I should be trying a distribution here, x is less than 4. So see how this word least and this word fewer, this one has it inclusive, whereas this one is just less than. So 1, 2, and 3 are what we're looking at. So we're just going to add up these numbers, the 1, the 2, and the 3, so 0.16, 0.1, and 0.08. So 0.16 plus 0.1 plus 0.08. Can we do that in our head? 0.24, 0.34. Yep, looks good. Use the table to justify why the Poisson distribution might be appropriate to describe this distribution of wasp nests. Ooh, okay, interesting. So this here, we could go to that, the thing we use Poisson, remember? And we say that it's proportional, it occurs randomly, they are independent events, or I should say occurrences, but I'm just going to keep that there. And the 2 S's means simultaneous, and then it just means occurs never. Okay. The other thing to bear in mind that it has to be discrete. So I actually like adding in, because it is a discrete distribution, right? It can only take whole number values. Okay. Use the table to justify why the... Okay, so I'm going to say, first of all, it's discrete. Amount of wasp nests is discrete. occurs randomly. So we can sort of justify that by the number of like them not occurring being quite high. So like we could even use this fact here. So wasp nests occur random. Oh, sorry, this should be rarely. Whew. Yeah, that's the problem with mnemonics. Occur rarely. Wasp nests occur rarely as P n equals 1 is equal to 0.51. Right, it shows that like, oh sorry, man alive, I'm going to turn my brain. Yeah, it shows us that the probability of there being no wasp nests in a whole hectare is more than half the time that happens, so it shows that it's rare. Okay, simultaneous occurs never. You can't, like a wasp nest, simultaneous occurs never. You can't have wasp nests don't overlap. Right, if there's like a wasp nest somewhere, there can't be another wasp nest in the same physical location. So yeah, we can use, but they did say use the table. So what you need to be careful of is see what they want you to use, and also be careful if they want you to critique it or justify it. So they're asking us to justify it, so we're giving good like reasons why Poisson is good, and they want us to use the table a little bit more. So we're sort of discrete sort of from the table. This here is using a fact from the table. The fact that they only gave us 2 lines means that I think that that's fine to get me the mark. Calculate the mean and standard deviation for the number of wasps nests per hectare. Okay. Let's use our calculator for this. There is several ways that you could go about it. So I think what they want us to do is get this table and chuck it into our calculator. So 0, 1, 2, 3, 4, 5, 6. So you can use your calculator to replicate these tables and then get data from it. So 0.51, 0.16, 0.1, 0.08, 0.06, 0.05, 0.04. Let's just check I've got that set up right. I'm going to be calculating, and I've got these 2 variables. Let me just set it. So the first variable frequency, first variable x list, y list. Oh yeah, I can never remember how to use this flipping thing. X bar equals 3. Expected value being 3 seems rather wrong, to be honest. 2 var frequency needs to be from a list. It's happening on this too. Okay, I got to explain this. So I'm looking at 2 variables. Am I? Yeah, I'm looking at 2 variables. Right. How often they appear is in the second list, and then the first list has what is occurring. So I think that should do it all good. Yeah, x bar 1.33. Yes, that looks about right. The reason it looks about right is because the number is going to be something close to 0, because 0 is our most occurring. But you do, yeah, this 6 is going to drag that number up a bit. So that seems about right. The other way to work this out is I could go 0 times 0.51 plus 1 times 0.16 plus 2 times 0.1 plus 3 times da 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 da. And so that there's looking good. So let's get our standard deviation. But I don't know if they want us to get like a... Oh man. These calculators do not make it easy. Does that seem right for a standard deviation? Not really. Zon. Yeah, that looks pretty good. 1.779. Should we just check the answers? Because I feel like... Okay. Mean. You shouldn't actually use mean because we're looking at a experiment. I shouldn't use this symbol. I'm going to change that to E of x. So the expected value, and it should be an n actually, it should be E of n, equals 1.33, and the standard deviation, I'm going to put a little s because it's a sample, it's an experimental rather than an actual standard deviation, and it's 1.7779. This is on page 43. Let's have a check, because I mean I should probably like do these things before I start teaching them, but I think it's better for me to show you like me trying to problem solve stuff. Okay, it looks like we got the mean right, but actually the standard deviation I didn't get right. 1.153. So let's just check if we got this one right. So most areas of 1 hectare have no nest, which makes, yeah, cool. Sweet, they were happy with that. Let's have a look at why my standard deviation was wrong. I already forgot the number. 1.153. If you're ever looking at the answers, like I just did, make sure you've had a go first. See how I've had a go before doing that. And then I'm just going to look down here to see if there was a place to get that number. So it's weird that I'm getting the correct expected value, but I'm not getting the right standard deviation, which is wacky to me. So, oh, here we go. The X list is on this one. Oh man, it is one variable. My bad. So it's totally. Hopefully, this actually teaches you a lesson. Yeah, I guess we're only looking at one variable. Let's try that. Okay, maybe the book's wrong. Yeah, so we've got X bar, which is it's annoying because we try and teach you the subject, but there's so much different notation for it. X bar is a way of saying the sample mean, right? But we say E of X, which means the expected value that the distribution takes, which is the same as the sample mean. And then in the answers they've used mu, which is pretty dumb. Well, I'm getting 1.7779 still, so maybe let's just say that the textbook's wrong. Probably makes the most sense. Okay, let's move on. Right. Okay. Use the mean calculated in D along with the tables or your calculator to complete the table to show the theoretical Poisson distribution of wasp nests. Okay, good. So the thing is with Poisson, normally lambda is the mean, and that is the square root. No. That is the standard deviation squared. Right? But they just want us to use this one value here, and they want us to make a model from this. So we're going to go ahead and assume that lambda is 1.33. And remember, Poisson only needs one variable. So let's go and find that. So we go back to distribution. So now we're modeling it. So we've looked at an experiment, and now we're modeling it. So I want to output, on this here, this table, these are points. The point 0, the point 1, the point 2. So we're not going to do cumulative, we're going to do points. So that's the P. So we want to chuck in a variable, and that variable today is 1.33. So let's fill out the table. First thing you should do is check that it's right. So see how they've given you one here? 2. So let's just check 2 and see that their thing is right. 0.233. You serious? What the heck? It's not even right. Okay, so what they've told us, they told us that is in fact, mu is 1.33, and we're using 1.33, so this should match up, unless I've done something wrong, which I haven't. X is 2, and lambda is 1.33. Yeah, alright. Well, first thing we'll do is cross off that one because it's wrong. 0.2339. Okay, let's fill out the rest. 0.2644. I'm just going to even put that lambda equals 1.33 here. Next one, we'll do 1 0.3518. Still look like they're going to add up to the numbers. 0.1037. When you're doing things like this, I have to keep checking. I did 3, good. 4, 0.0345. Ooh. Ooh. Okay. Oof. Yeah, I should probably get a lesson on this now, just because I'm here. Why not? What the heck does 9.72e negative 03 mean? It's horrific notation that the calculator makes us... Like, what's the point in having notation like this? How hard is it to just write out the number? Anyway, this e just means times 10 to the power of, which they could have just put there, like times 10 up arrow, right? Rather than us having to learn what e means. But anyway, think engineer. Engineer is like the number 10. Okay, what I do, if it's negative 03, I just move the decimal point backwards 3. So I'm going to go 1, 2, 3. So that means the decimal is going to go to here. So we then fill the gaps with 0 and put a point there. So that's the number that we are looking at. Right? So it's going to be 0.009. That means I think that the next one's going to be so small it's irrelevant. Oh no. Same thing. 0.002. Right, so now we've got the table filled out, and what do they want us to do? Use the done. Okay, discuss whether a Poisson distribution is a good model for this distribution of wasp nests in the national park. As part of your discussion, you should compare the features of the observed experimental and model theoretical distributions. So what we need to do is compare these numbers and see if they do a good job of modeling it. Do you know the funny thing is, we would make a way better model if we just made lambda smaller, but it would throw these last ones out a bit. So you can see that there's a really, it's a bad, 0 doesn't do good at modeling it at all, it's half the value. 1 is not a good model because it's the other way around, the experimental is half that of the model. Then 2, the model is, again, the experimental is half that of the model. Then at 3, you're getting, it's fairly close, but it's not great, to be honest. Yeah, this is a horrific model. Is Poisson distribution a good model for the wasp nests? Okay, I mean, I could write these things down, but I don't know if this is actually going to be that helpful. So let's just go through and make a list of overestimation. So we should talk about how the model does. The model underestimates the amount of no, it's not an amount. These are proportions we're looking at. The proportion of hectares with 0 nests. We can write by 0.51 minus 0.26 equals 0.25. And then from there the model always overestimates, or nearly, but not quite. I kind of wanted to make a blanket statement that the model then overestimates for every other amount of wasp nests, because it does on 1, 2, 3, but then it doesn't on 4, 5, and 6. So yeah, the model overestimates the proportion of wasp of hectares, maybe I should just write hectares, proportion of hectares with 1, 2 or 3 nests, and then over estimates the rest. No, let's just say, no it doesn't, it underestimates. Dang it. Estimates 4, 5 and 6. The model is too far out on the first few to do a good job. Perhaps a lower lambda value would be an improvement. Okay. It's probably too freaking messy for you to read. You can pause that, try and read it, or just maybe chuck subtitles on and see if Google can understand my accent. Yeah, that's page 43.